Alright, I am here with Steven today, and we are going to work on this problem here. So, starting with Gauss's law, calculate the electric field due to an isolated point charge of Q.
And we're taking this from page 246 in your book, example 24.4, so you can look at that if you want to have the book's view on it.
Right, so if I start with a very simplified diagram here, we used to have our tiny point charge there, Q. And what we want to do on this kind of problem is we're basically going to want to apply Gauss's law to figure out what the electric field is. And so, but at a distance r away from it. So if I go ahead and draw this line here. So
basically
this
what we want to know is just
r.
the general electric field, which will be in terms of R.
Yeah, and so in order to actually take advantage of Gauss's law, we will want to create a highly symmetric Gaussian surface, which is basically this arbitrary surface, which, let's see if I can do this, which we could basically use like a sphere, for example. Okay, so we have this 2D map of the sphere here. So what we're basically going to do is if I take this picture and I look at the electric field this distance r, if I were to zoom in on this picture some and kind of give you a better idea of what's going on here. So we have this surface, and the closer and closer we zoom in, the less curvy it gets. So we have the electric field E pointing outwards of it. And then since I'm also looking at such a small instance, I can also look at how the area changes and how it's orthogonal to the actual curve. Right, and so from this diagram we can see that E is parallel to A. E is parallel to dA. And so now
what we've done here is we're basically saying from the point charge Q in all directions, electric field just goes straight. So we've taken one part of the sphere and the electric field is going straight through it. And dA in this case is perpendicular to the surface of the sphere, and so is the electric field since it's going straight through it.
And so now if we actually look at the definition of Gauss's law, so Gauss's law, or actually rather the flux through a surface by Gauss's law is equal to E dot dA integrated over the entirety of the surface. But luckily, since we're on this kind of problem, you don't actually have to do this hairy kind of integral. And since E dot dA, or E and dA are parallel, the dot product is just equal to the sum of them multiplied together, and then when integrating dA we just are left with A. If that made any sense to you, perhaps.
Where are you gonna see?
Here. So E is constant everywhere, and I can take it out like so.
So then we're just taking the surface integral of dA, which is just A.
This is like the example of if I just integrated dx, I get x.
But we're taking surface integral, so since it's area, that's a surface. That's how we're getting just to A.
Yeah.
So you just take the E out of the integral because they're parallel, so the dot product pretty much just goes away. And now you get that simple solution.
Okay. And then also the other part on Gauss's law is that it's equal to the charge enclosed divided by the constant epsilon naught. So at this point now we have something that we can actually work with, and it's not too bad either.
And this is generally what you're going for in any Gauss's law situation. You're just trying to find a surface, a Gaussian surface, that you can simplify Gauss's law to get EA or some variant of it. Because here we've taken a point charge, the electric field expands spherically around it, we've taken a Gaussian surface of a sphere, so at all points E is parallel to dA, so it just gets rid of the integral, and we're left with a simple 4-variable equation.
So now at this point we want to go ahead and solve for E. So what I'm going to go ahead and do is divide both sides by A, so I get E is equal to Q enclosed over epsilon naught times A. Now, what is A? A is just the surface area of this sphere. And so you can either just believe me that it's 4 pi r squared, or another way to remember it is by looking at the volume, the cube, 4 pi r cubed. And if you differentiate that with respect to r, the thirds will cancel, degrade the power by 1, you get the same thing up here. So that, I mean, if you walk into the AP test, though, that equation will be on there for you to use. And so now at this point, we've basically solved the problem just by substituting what A is. So A is 4 pi r squared, so E is equal to, I'm going to see how well I can write this in such a form, Q enclosed over r squared. And I also notice there's 4 pi and epsilon and 1 on top. And so, you know, people have realized, oh hey, this shows up so much, let's go ahead and create a new constant for it.
Which
and
was actually recognized probably earlier.
Yeah,
from
Coulomb's constant was thus born.
So, yeah.
So, yeah, done this problem. This is the end credits. It.